Okay, good morning. So we continue the discussions. Now what we are going to look at is the solutions containing parameters. What do we mean by that? Suppose you have the problem D. So you have the initial data x naught, y naught, and what we have proved is that over the x naught minus h to x naught plus h, there exists a unique solution whose integral curve can be drawn something like this. Now this particular solution has the initial data x naught, y naught. Now we keep of course x naught fixed, but y naught could be different. So what you do is the solution yx of y derivative equal to f of xy satisfying the initial data yx naught equal to y naught is henceforth designated by yx y naught. That means that x naught, the function y satisfies the condition y naught. So let me just write yx. So y naught becomes a parameter. Okay, right? For example, if you look at this equation, dy by dx equal to y, with the condition that y 0 equal to y naught, then you know that the solution of this equation is y naught e to the power x. Now when you change the initial data, it's the same solution, same format in which it appears, but y naught appears as a parameter. Okay, so that is incorporated in the description of the solution. So what is the problem? The problem is this. It's actually corresponding to a physical problem, because in the physical problem you see that the initial data comes from what is called measurements. Okay, suppose you are computing the position, there could be some error in the initial computation because there are limitations for your instruments to mark a point accurately. So there will be invariably some error coming into this computation. So physical problems do carry a certain kind of errors. So your actual problem may be something, but the problem that you have would solve is something totally different. Totally different in the sense that the initial data may be slightly coming out with an error. So one of the questions that you ask is this: is it sensible to use this solution as a approximate solution to the actual problem? Okay, this depends on y naught. So what one tries to analyze is this: suppose the initial data is changed to something like this point is x naught, y naught data. Then you know there is a solution for this problem passing through this. So actually, if you were to use the solution with the initial data y naught tilde, then you are going to get a different solution for the problem, and it will be what is the error that you occur. Suppose you want to compute y at a particular x. This is the actual value that you are expecting, but what you would be computing will be this particular height. Are they close enough? Once your initial data is close enough, are they close enough? So what is the dependence of the solution on the initial data? Okay, right? So this is the problem that we are going to consider, and this is very relevant physically. So when you change the initial data slightly, can you assure that on the interval on which the solution exists, the solutions also stay closer? Then of course, if it is within the error that you have, for example, look at this particular solution. Now you see that if you look at this particular differential equation, then what you have is this. Now if you take the initial point as, see, this is some y0, then the solution is something like this, the exponential function emanating from that. Okay, that's what you have. Okay, oh, this is y0. Suppose we use a y0 tilde, then you see that it's a different solution. And as you see in this particular problem, you see that as x becomes larger and larger, the yx is going to differ considerably. So there is a limit to which, within which you can use it. It depends on the problem, where you will have a certain error that is acceptable, and depending on that error, your interval will remain. On the other hand, see, this is the population growth problem or something. Suppose your problem is something like this, dy by dx then what is the solution? The solution is again y x y0 is given by y0 into e to the power minus x. This is the solution of the problem. Now this is what is called the radioactive decay problem. In this case, what you see is that as x increases, now if you draw the graph of this function, try to draw this graph of this function, then you see that as x becomes larger and larger, the two solutions get closer and closer. So you see that it is immaterial if you make an error. You can allow room for a bigger error initially, so that the solutions do stay closer after some time. After a long time, if you are measuring, it does not really matter at all because of the nature of the function. So one of the problems that you ask generally is that what is the dependence of the solution on the initial data? Okay, so we first prove a theorem which says that where a solution exists if you have an error in the data. Let's once again look at the problem. You recall that rectangle that we have drawn here. This is the point x0, y0. We have assumed that f is bounded by m, and then you see this is suppose this is h, this is mh. That's how we have taken it, and you see that the slope of f or the bound for f lies in this particular region, which simply says that if you take a point here and draw the line segment or the arrow with the slope f of xy. Suppose this is the point xy, that this is a slope f of xy here. Then you see that mod f of xy is less than or equal to m. This condition. What does it say? This arrow would, or the direction would lie inside this region. Not only that, it has the slope less than that. In fact, you see that all these arrows are like this. The consequence is that any solution will stay within this region. It can also be staying like this, or depending on the particular solution. Okay, depending on what is the direction field that you have. It's the same case over here. That's how we have chosen the H. Okay, so that the graph or the integral curve of the problem or the initial value problem will be completely lying within this particular cone region. Okay, that's what you have. Now, what we are going to face is this. Initially, suppose you are changing the initial condition. When you change the initial condition, it is the same condition. So what do you have? Suppose I change the initial condition within this bound. Then what do I have? The slope of f would be controlled by this line over here. And the slope of this will be controlled by this line. Therefore, what is the interval on which you can assert that there is a solution? It will be the minimum of what you get here. It will be on a smaller interval. See, the moment you move from here, the initial data, the solution will be will be defined only on a smaller interval. Okay, so the sort of estimation of the error will be determined by how much, on what interval you will be getting the solution defined locally, and also what is going to be the error that we can estimate. So let us work this out. So you have the following theorem. Let me make the statement of the theorem. I hope you understood the problem. That is, this y0 is appearing as a parameter. What is the nature or dependence of the solution on this parameter? That means if you change y0 slightly, will the solution also deviate only slightly? Or how much it will differ? And these kind of estimations are relevant in a physical problem. So we have the following theorem. If f of xy is continuous, we write yx and satisfies a Lipschitz condition, on y for and then there exists a unique solution in the region H prime where H prime equal to minimum of A and B by 2m, m being the bound, okay. So what does the theorem say? Theorem says the following. Okay, so what you have is this. So you have a now you have a rectangle with the sides given by 2a and 2b, and x naught y naught tilde is symmetrically placed. That means this is a, this height is b. Now suppose we alter the initial data. Initial data is altered with this restriction. What is it? That okay. The initial data is within this region. Okay, that means y naught tilde is, or the initial data y naught is within this particular thing. So this is going to be b by 2. Okay, so your initial data, that is y naught, is lying on the segment with a, this is y naught minus y naught tilde minus b by 2 and y naught tilde plus b by 2. or this point is x naught, this, and this point is x naught. Okay, so it is somewhere on this place. So your y naught is going to be somewhere on this place. That is what this says that. Okay. Yeah, this is the restriction that you are having. That is, within this region, that means between y naught minus plus b by y naught minus b by 2 and y naught minus b by 2 or plus b by 2, we are going to choose the initial value y naught. Okay, then where the solution will lie? We are assuming that f is bounded by m. Then what do you have? See, from here, okay, let us assume this scenario. See, if you are going to look at the solution starting from this point, then it is going to lie, or we can assert for sure that the solution lies on x naught minus h to x naught plus h, where h is the minimum of a and so what you are asking is, now suppose you are shifting your initial data within this range somewhere. What is the interval on which you can certainly assert that there is a solution? See, you go halfway through this and then you see that f is bounded by the same. Therefore, this is going to be something like this. Therefore, what is this distance that you get? The distance that you get would be half of this distance. So if you are somewhere here, you will get on a larger interval. Still, this suppose y naught is somewhere here, and then if there is a positive distance between y naught and y naught tilde is going to be within b by 2. That is what you have. Y and y tilde. It is going to be a point within this region. Then you are going to have this. So what is the h prime that you are going to have? What you get is that this h prime is equal to minimum of, we are giving an estimate. It may be on a, see, depending on y naught, suppose y naught gets closer and closer to y naught tilde, then what happens? You see, the corresponding solution will be defined on a larger interval, but certainly something less than this this h that you have. This is your h that you have. Okay. Therefore, what is the dependence of the function on the parameter? This is the question that you have. Now, it's quite easy to prove this. Now what you do is, proof of the the existence and uniqueness theorem. Uniqueness theorem. To the point x naught y naught, with the condition that y naught minus y naught tilde e by 2. Then you see that this h prime that you get is certainly going to be uh, greater than or equal to h by 2. So it lies between h by 2. That is what I said. If you keep this point closer to y0 tilde, then you are going to have this. You see the extent to which the solution will the integral curve will grow is controlled by this one, this line, these two lines, and therefore you see that on a larger interval it is going to be true. So you just use this theorem, then what you get is this, that is h prime is not less than provided y0 belongs to that is one result. Okay. So that's about the estimation of this. Suppose we vary the initial data, then how far the solution, the interval on which we can assert the solution exists. It does not mean that it will not exist on a larger interval. It may exist on a larger interval. Okay, that is certainly possible. Yeah, but minimum, at least on this interval, you are assured that there is a solution. So the next theorem. F be continuous and it fits with certain k. If designate the solution of y derivative equal to f of xy not exists for some rectangle R with mod x minus x naught less than or equal to h mod y minus y naught L then y x continuous in both the variables continuous in the region this is R. If the solution exists, what we are going to prove is that the solution is a continuous solution. The proof is very simple because we can make use of the fundamental inequality to prove this result. So what we are assuming is that this equation has a solution whose integral curve lies in this particular rectangle. That means for mod x minus x naught less than or equal to h, y minus y naught less than or equal to L, then you see that this particular solution that you have is continuous in the region R. Okay, let us prove this result. It's quite simple to prove this result. So you see that you have a rectangle now. It's a different rectangle that you are talking about now. Mod x minus x naught less than or equal to h, mod y minus y naught less than or equal to L is a rectangle R on which you see the solution, the graph of the solution exists. Now what we are going to assert is that if you take a point on this curve, okay, so what does it say? Says that of course we have the function continuous with respect to x. There is no problem about that. What about its variation with respect to y naught? That means suppose we change y naught to a neighboring point, will the solution also stay closer? Or in other words, we are looking at the continuity of the function y on the rectangle. Okay, so let us if y x y naught 1 and y two solutions of the initial value problem. That is dy by equal to f of xy with y x naught equal to, this is not derivative, and you have a second problem, two initial value problems. This y naught and y naught 1 and y naught 2 are different. Okay. Okay, we assume this also, that is y naught mod y naught I minus y naught tilde is less than or equal to n. This is something that we assume. Okay. For I equal to, okay. Then what do you have? The fundamental inequality. See, these are two solutions of the same equation with two different initial data. So what you get from the fundamental inequality, this is what you have: y x you know that both of them satisfy the two different initial conditions, but both are exact solutions of the differential equation. Therefore, the second term, which involves the error in the fundamental inequality, would be 0, whereas the first term will involve a term like this: mod y naught e to the power k. Now h is the interval on which the solution exists. This is using the fundamental inequality. In fact, you have seen this, that these two, that is y, x, y naught 1 minus y, this is less than or equal to, there are two terms here. One is, of course, the evaluation of this at x naught, which will give you y naught to e to the power k into mod x minus x naught, this is one term, plus epsilon divided by k e to the power k. This is the estimate, this is the inequality that you have, and you see that epsilon is equal to 0 because you are considering both as exact solutions of the differential equation. Therefore, this term would be 0, and it will be mod y naught 1 minus y naught 2 e to the power k x minus x naught, and this can be replaced by a higher estimate, namely mod x minus x naught less than or equal to h. Therefore, this is okay. So what is the implication? That is, continuous uniformly in y naught for mod x minus x naught already this function is continuous in x. For any value y naught, it is a continuous solution on this interval. Therefore, it follows that on R, this particular function is continuous with respect to x as well as y naught, or the simultaneous continuity of both of the function y with respect to x and y naught. Now, the geometrical meaning of this is that the two integral curves, if they are initially lying close, then they stay close. So, if you have two function solutions starting from here, this is y naught 1 and this is y naught 2, then the two solutions will stay closer over the interval mod x minus x naught less than or equal to h. That is the geometry of this. Now the next theorem that we prove is the following. Suppose, or rather I don't want to prove it because the proof will take some time. See, this is the assertion of the next theorem. That means, suppose you are assuming some extra smoothness of f with respect to y, like Lipschitz continuity is there, but otherwise you also assume that f is the partial derivative of f with respect to y is continuous. What can you say? How does it transforms or translates into certain smoothness on the solution? So this proof, I leave it for you to look into the book. So I'll say what the theorem is. The theorem is this. Of the previous theorem. If in addition the partial derivative of f with respect to y exists in the and is continuous, then the solution see, there we have proved the continuity with respect to the second variable or the continuity with respect to both the variable uniformly. Okay, but now we are going to prove this, or we are going to assert a much more stronger result, namely if f has the property that the partial derivative of f with respect to y exists in D and is continuous, then you see that there is the corresponding smoothness for the solution with respect to y naught. Okay, that is the partial derivative of y with respect to y naught exists So there we have proved the continuity, that if y01 and y02 lies closer, then the solutions are also going to lie closer. Okay. Now we go one step further and say that if f is not only continuous but the partial derivative of f with respect to y exists and is continuous, then you are going to have some more smoothness for the solution with respect to the parameter. Okay, so obviously the smooth your function is there is a corresponding level of smoothness on the solution that you get, not only on the as a function of x, but also on the parameter y0 or the initial data that you impose on the problem. That means when you go closer to, or y2 initial data lie closer, then the solution is going to lie closer. This is the conclusion. So I refer you to the proof given to this theorem in page 13 of 4H. Now finally we will have another result. See, until now we were talking about how close the initial data is taken closer, will the solution also stay closer. That we have taken, and we have also looked at the dependence of the solution on the initial data. Now what we are going to prove is the following. Suppose you have the equation f of x y, the initial value problem yx not equal to y0 in some region D. Suppose you have another problem same initial data with the additional assumption that capital F and small f are lying closer. Something like this. Then what we can say is that the solutions of these two problems, suppose I denote this, the solution of this by y, the solution of this by y tilde, then these two solutions are also going to lie closer. Okay, so let me state the theorem now. Statement of the theorem. In some domain D, continuous B f of xy satisfies Lipschitz condition on y with constant k we are not assuming the same condition on capital F. We are assuming small f to be Lipschitz with respect to y, and then f of xy D for some x0 belonging to D, yx and y tilde x are admissible less than or equal to h and satisfying yx corresponds to a initial value problem with y naught as the initial data, and the other one with the initial data y some okay, y naught and y are both solutions of the with the same initial data. Okay, so it's that. That means both satisfy the same initial data. That means the integral curves corresponding to both the functions pass through the point x naught, y naught. Of course, we are assuming only small f is Lipschitz and not the other one. Then okay, what does it say? There are two equations now. One like this, I mean, as see exactly what we did in the case of improving that general situation where the function is not assumed to be Lipschitz. Okay, there we approximated the function by a polynomial which is Lipschitz. Okay, now we are going to have a similar scenario. You have an initial value problem where f is assumed to be Lipschitz. Here, I think this is capital F. Sorry. Capital F. Yeah, that was a mistake. It's capital F. These are two initial value problems now with the same initial data, but the equations are different. And there is a sort of condition that is given, that is f and capital F are lying closer on D. Then what we assert is that y and y tilde are also lying closer, and the estimate for the error that you have is given by this. So let us prove this. I mean, proof is very simple. Note that is an approximate solution of with error let us compute this. So what you have this d y tilde by now this you write as f of x y tilde minus add and subtract these two terms. Okay, then what do you get? You get But we are assuming that this is less than or equal to epsilon for every xy belonging to this. And we have assumed the function is that both y and y tilde are admissible functions, by which you mean x, yx belongs to D, x for mod x minus x naught less than delta. Therefore, this is, see, both xy, xy tilde is in the domain, and this is f, capital F is defined at that point, as well as small f is defined at that point. Therefore, you have the estimate C valid. Okay. And now what do you have? So you apply inequality. Then what you get is this dy tilde by dx f of xy tilde is less than or equal to epsilon, whereas y is an exact solution of this. Therefore, and both satisfy the same initial data. So in the inequality, the first term will not matter in the inequality. So what you have is this: you get mod yx minus y x tilde or y tilde at x is less than or equal to, the first term is 0, the second term is epsilon divided by k, that is the error term, e to the power k h minus 1. This is the estimate that you get. Okay, so that completes the proof of this theorem. Okay, therefore you can always replace the equation, original equation, by another equation which may be easily solvable. I will give an example. An example is this. It's also this. See, if you look at this example, look at this example. Y derivative equal to sin xy. Now you take some rectangle on which this is different. This is a very nice function. You see that at least in the neighborhood of 0, 0. Okay, right? Sin xy is approximately equal to xy. Or even, situations like, suppose you take x equal to 0 or y equal to 0. Along this line also they are very close. So you see, somewhere in the neighborhood of this line or in the neighborhood of this line, sin xy can be closely approximated by xy. Okay. Therefore, one can solve the equation y dash is equal to xy with the same initial data. Okay, something like say y, or the other one is y0 equal to some y naught. That means suppose you estimate take y0 as some point on this. So this is 0, y0, and then look at the solution of that. So this function can be closely approximated by xy in the neighborhood of this line. There is no difficulty. Okay, and this one you see is a very simple equation. It's a linear equation. Okay, right? And one can solve this. And the solution of that will be lying closer to the corresponding solution of this particular equation. That is what it says. Okay, so this is what you mean by the dependence of, or the approximation of a equation by another equation and finding out the solutions. Okay, let me stop here, and then in the next lecture we will be thinking about extending the solution. So far we have worked on, we have said that locally a solution exists. Now the next stage of the next question that you can ask is, can you go beyond that x0 minus h to x0 plus h? Is it possible to extend the solution beyond that? We will look at this problem in the next lecture. Okay. Thank you very much.